from NICT, and I'm a co-chair of this TPC co-chair of this workshop, and it's my great pleasure to serve as a chair of this keynote speech session from Mr. Beckman, and he's from Brocade, and he's also serving as a chair of the ONF Open Database Working Group. And today his talk is on the model-driven mechanisms for OpenFlow device interoperability. And I think we can hear about the future direction of the SDN technology, especially focusing on the power of the abstraction. So let's welcome him.
Thank you. I think I have 2 mics. Maybe we can use that for questions later on. And this is working, right? Sounds like, okay, thumbs up. Thank you very much for having me. I'm very pleased to be here. This is definitely a little bit different audience than I'm used to talking to. It seems like much more often it's customers or operators who kind of look at SDN a bit more from the outside, like what can it do for me and that kind of thing, even though I spend my day much more trying to figure out how to make it work. I should give you a little bit more about my background because that'll turn out to be a little more relevant later on. When I was first getting involved in networking in '95, I was a chip designer. And so I got into networking very much at the bottom at the packet processing level, and mostly layer 2, just a couple of years later doing more layer 3 IP forwarding. But anyway, slowly moving up the stack, and I went into storage networking for a while, being at Brocade. That may not surprise you. I am working as a chair at the ONF and the Open Data Path Working Group. I also am a project lead at a small project, but a related project at OpenDaylight. So it's kind of important, I think, to cross some of the bridges, and I see a lot more of that going on now in the industry, which is pretty interesting. And it's also interesting, it's not really part of my presentation, but I know we have a panel later today that's kind of, here the workshop is called an SDN workshop, EWSDN, and then the question is SDN dead? Long live NFV? I don't know if that's still the panel topic, but it's kind of interesting in the context of this talk, or this talk in the context of that question. So I did the abstract, you guys. I hope I've seen the abstract. I won't go into that a lot, but basically, yeah, that we're going to look at how models can alter the way we make use of OpenFlow. And it turns out we need a new way to work with OpenFlow because the early model was great for the beginning, but we need to do something that works more complex. Now I thought that there was an academic focus here. I'm not sure that my original perception was correct, but hopefully there are a number of academics because I think it lets me talk about things a little bit differently, which I've been very eager to do for a long time. There are a lot of challenges around SDN on an implementation and deployment perspective, which maybe doesn't seem like of particular interest on the academic side, and yet solving these problems I think will really make use of academic horsepower and ideas. So anyway, here's what I'll talk about. I'm going to talk about device pipelines. It didn't actually say that directly, but that's the modeling that I'm talking about, is to model device pipelines. And that in turn causes a change in the OpenFlow framework. OpenFlow framework didn't really talk about device pipelines at the beginning, but it needs to. And then we've gone through some iterations in how we have architected this framework. We'll talk about that. That's kind of the progress that's been going on. And I think where this heads is into header space analysis. And I get there right at the end of the talk. And I'm not an expert on header space analysis. I kind of get the idea of it. I think it's exactly what we need to do to really take this framework that we have constructed and make it scalable and really drive adoption So essentially, in order to make all this promise of SDN compelling and make sure that it's not all about NFV, I mean, I think NFV needs SDN, and SDN can also do some other things. Not that I'm also a fan of NFV, so just to be clear about that. So background, you know, the SDN promise has been to decouple control and data planes and do that in an open way, so that not just that it was an open standard that you could publish it, but that there was enough clarity in the standard that you could buy your control plane intelligence software probably from one vendor and connect that up to another vendor's hardware, kind of in the way we can buy hardware and software from different vendors in the compute space, right? And OpenFlow was brought forth. I mean, I know in the early days it seemed like OpenFlow and SDN were almost used as synonyms, but the idea was that OpenFlow is this low-level open protocol that allows us to build SDN. And you know, maybe there'll be some other stuff too. And in the early part of OpenFlow, in OpenFlow 1.0, the model was working pretty well. A lot of vendors produced, you know, OpenFlow-enabled devices. That is, they had existing devices, and they added OpenFlow drivers to their existing devices. They didn't need to change the device. The idea was, you know, OpenFlow can manipulate in common ways how devices forward. Devices already forward, but right now they're controlled by, you know, algorithms that are that live inside the boxes, and we don't get to manipulate those from outside the box. And that would be desirable, given all the growth that's happening in cloud and all virtualization and so on. We need a different paradigm than to just expect the network to be responsive. We want a different model. Plus, we want vendor independence. We being the buyers, the people with that are paying for all this, really, right? So many vendors offered those offered OpenFlow-enabled devices. It was a single table model, a single OpenFlow forwarding table. And then right at the end, right before the ONF was published, there was a new OpenFlow version produced like the week before with multiple tables. A few details to work out. I think they just passed that on to the ONF, and the ONF says, oh, this will be great. And then a lot of interest turned, you know, the visionaries turned a lot of their activity more toward programmable data planes, which I'll touch on a little bit later on as well. So I mentioned, I started this by saying pipelines, and then went back to some earlier background. So in terms of a pipeline, packet processing in ASICs is done at a series of, it's a state machine. There's a series of stages. Packet, first a lookup happens, and then another lookup, and decisions are made, and so on. The pipeline from OpenFlow 1.0 perspective was trivial. It was a single table. We do one lookup. It could be a very complicated lookup. Actually, we do a prioritized parallel lookup, but you know, it's what in ASIC terms is called a TCAM, a ternary content addressable memory, that can sort of look at everything at once and figure out what the best match is. So one single lookup, take the best match. Based on that match, we decide what we're going to do with the packet. That's it. One pass, one stage in the pipeline. That was the good news about that is nearly every device had this kind of TCAM table. Normally, it was the access control table, and so many vendors can take this single stage model and just somehow associate it with their TCAM pipeline stage and implement that early OpenFlow on their device. So that was the really good news about OpenFlow 1.0. And indeed, we saw lots of devices, and things interoperated pretty well. And the bad news is that it's kind of limiting to have that single stage pipeline. There's a lot of things you can't do with that single stage pipeline, and scaling is very difficult. So this is depicted by our complex pipeline graphic there. And now things get more interesting. So as I mentioned, the OpenFlow 1.0 limits were noticed early on, even before the ONF, and so the sort of ad hoc group, largely Stanford, but a number of other folks as well, including folks in the industry, not including me. I wasn't involved until the founding of the ONF. They said, okay, we need to add more tables. That'll solve it. If we put more tables in there, we can do all kinds of things. That it turns out you can. Yeah, it's quite true. So they published OpenFlow 1.1, and they did this, like I said, the week before the ONF was launched. And I'm sure that they felt, you know, if we don't get this published, our work will be kind of lost in the confusion of the ONF launch. And they probably were right. But in the process, they bypassed a policy that they had, the sort of a working policy that they had, that before they finalize a spec, a version of OpenFlow, they would make sure that they could implement it in working code and maybe fix any glitches or gaps in the spec. They didn't have time to do that, so they bypassed the working code policy. And unfortunately, the ONF picked up on that, and for the next couple of releases also bypassed the working code policy. So OpenFlow 1.2, OpenFlow 1.3, those were both published without any effort to deliver working code. On a related note, it's not on the slide deck, but OpenFlow 1.3 was published 3.5 years ago, roughly, and it was only a few months ago that the ONF published the first basic conformance test. So the absence of working code made it quite difficult to develop a conformance test, in part because we realized, well, not every device is going to be able to support this. This is a lot of what we anticipated in the folks that got together to form what was the precursor to the Open Data Path Working Group. That's called the Forwarding Abstractions Working Group. We kind of anticipated this. We looked at this multi-table model and we said, hold it, how do I figure out how to map that into my switch? If I'm trying to write a driver in my switch, I can't figure out how to do that. There's too many variables at runtime. Essentially, the OpenFlow framework, this first bullet here, it says the model is the controller just tells the switch what to do. And the switch just has to deal with that. And when we have multiple possible pipelines, a sort of almost infinite possible pipelines, then the switch doesn't really know what the controller's plan is. So we'll take a look at some of these potential pipelines. Both of these pipelines, actually, the graphics are out of a Broadcom publication that I'll talk a little bit more about, and you can see the link to it there. In a sense, each of these pictures is an abstract pipeline of how we may want to process a packet. One of them is focused on MPLS, the other one's focused on layer 2 and layer 3 forwarding. There's actually a number of other pipelines that are very interesting. In fact, you can say there's dozens or hundreds, but even once you get up to 2 or 5 or 7, and the other thing I should say is, so these are Broadcom's version of these pipelines, but if you talk to somebody else, they might leave a table out or put another table in. Maybe they'd arrange them in slightly different order. There's more than one way to approach any particular networking use case. And different people come at it different ways. Maybe they want to scale in different ways. Maybe they're more focused on performance, or they're more focused on bandwidth, or they're more focused on number of endpoints, or low cost or low power. There's just, depending on which way you optimize, maybe they want more flexibility. They want to be more extensibility. A lot of different variables might drive different decision making. And maybe it depends on which products you already have, or which, what ASICs you're using, what vendors you partner with. So from the switch's perspective, if you get a message that's supposed to go into, say, table 2, it kind of matters whether it's this table 2 or this table 2. It changes how you may try and put that into your underlying device, because the underlying device may have a completely different pipeline, but it may still be able to, it may be a superset. Very often that's the case. Your underlying device has a pipeline that is more capable than the use case. Of course, that's normally the approach, because device vendors try to make their devices cover a number of use cases. Not all use cases, but they want something that they can sell into multiple markets. And so the underlying device will have a kind of a rich pipeline, and any single use case will have a smaller pipeline, and usually you can figure out a way, and usually that's done through all the drivers and protocols and so on. They figure out how to implement this simple pipeline, or maybe that simple pipeline, or possibly both in the same underlying physical pipeline. So, and that's all done during product development. You're well aware of which pipelines you're trying to support. You know you want to do that and you want to do that. You know what your underlying chip pipeline looks like, and that's the developer's job, is to figure out how to make all that play together. So as I mentioned, these are two different kind of abstract pipelines. As it happens, a lot of Broadcom devices do support both of these pipelines at the same time, and in fact they support several other pipelines at the same time. Indeed, the underlying pipeline is much more complex. Here we see, say, 3 tables plus what in OpenFlow are called group entries for other sort of processing near the end of packet processing. This one's got 7 tables. The Broadcom device itself has something like 25 tables, not the device, but the device pipeline. So dealing with pipelines and dealing with the variety of pipelines makes life quite difficult. If all of our switches, and routers, all of our devices were based on network processing units, this wouldn't be a problem. We would just, at the ONF, we would just say, you know, all the features are required. It's all software anyway. All these features are required, and then it would be much easier to write a conformance spec. You know, everything is not an NPU. We have a lot of ASICs out there. Most devices, especially most deployed devices, there's quite a variety of NPUs, but they're just not in that many places in the infrastructure, in today's infrastructure. And if we say, well, basically you can use SDN if you swap out all your infrastructure, that's a difficult adoption model. And basically, it's not going to go very far. Meanwhile, we've seen folks like Google and Internet2 have used classic legacy products in an SDN situation and done interesting things. So it's not really fair to say, well, you can only do SDN on NPUs. So definitely we want to be able to figure out how we can make SDN work interestingly on ASICs. And of course, we're also interested in NPUs and potentially future devices as well that maybe fall in between ASICs and NPUs. There are people call them programmable ASICs. They may not be software oriented. In fact, they probably run faster than NPUs. They're faster than what are often called run to completion, which means that you don't quite know when the code will finish because the code may change, for one thing. I mean, it's kind of, it may loop, etc. Where ASICs typically have a well-defined pipeline. Even the programmable ASICs, what they talk about is rearranging what each stage does, but not necessarily rearranging how many stages there are. Maybe a little bit, but there's still a fixed number of stages. In some cases, they may loop. In that case, maybe it starts to resemble run to completion. And then there's, even if we do have lots of programmable ASICs, they won't necessarily all be the same, so we still have a little bit of a challenge. We can't just require everything in the OpenFlow spec. We have to figure out how we're gonna, what maps to what devices. Just as today we have a challenge of figuring out what runs in what ASICs, even with future programmable ASICs, we'll still have to decide what runs. Most things will run in most ASICs in that future world, but not everything will run everywhere. And in any case, we don't have those NPUs everywhere, and we don't have programmable ASICs everywhere. Maybe we don't have programmable ASICs anywhere yet, but I'm told they're coming next year. And it'll be another interesting world at that time. However, I want to say that this is, part of the reason I mentioned that not everything will run on every programmable ASIC is to say that the problem we're dealing with now is sort of a durable problem. It's not like, well, why bother, because next year the problem will be gone. That's not the case. Next year the problem will still be around, in part because those programmable ASICs won't be everywhere. We don't know what they'll cost. We don't know what the tool infrastructure, and there's a huge ecosystem that's going to have to go in around those programmable ASICs. So I'm one of those practical guys. How do we make use? How do we really scale up what SDN can do on today's ASICs? Not just my company's ASICs, but other companies' ASICs. We use vendor merchant silicon ASICs as well. So how do we make this work? I'm very lucky. I work at a company that's quite serious about OpenSDN, mostly because they see that as being good for them strategically. So, well, that's a good reason. From my perspective, it just means that I get to work on interesting problems and you know, in an open model. I was just talking with EDUARDO before about, I'm also part of the ONF, Open Networking Foundation, and I just wish it was as open as a university is in terms of, you know, how you can get in and get out and talk to people and so on, and not everything involves NDAs and intellectual property agreements and so on. So that's kind of my philosophical bias toward open, and so like I say, I'm very lucky to be at Brocade. So practically, how do we make SDN really interesting on today's devices, and also, you know, create this path forward? Actually, as we solve these problems and grow the deployment of an SDN model where there's cluster-based controllers that are sort of logically centralized and connected to a sea of devices, that ecosystem will really lend itself to the future devices that are being envisioned right now. All right, all that still is background on this pipeline model story. I mentioned already that the original OpenFlow pipeline was trivial and, of course, abstract. There's not really device pipelines that look quite like that OpenFlow model. And then we have this diversity of real pipelines, the pipelines that are you know, in our wiring closets, in our boxes, from a variety of different vendors, some multiple generations, some old, some new, and some higher end and some lower end. Meanwhile, as we want to enable SDN, we want to create an environment where you could write code, you know, where you have a well-understood API, a well-understood, you know, you have to make some assumptions about what the devices can do. We don't want to be programming for different devices. We want to program for an abstraction. Just like on the compute model, you can write code that uses graphics functionality without knowing which graphics chip is in the box, right? You can write it and just say, I'm writing it for Windows or I'm writing it for Linux, because Windows and Linux offer us these nice APIs. We need that kind of abstraction. And our proposal is, you know, basically those of us that were involved in the early days of the ONF, or the early days of the forwarding abstractions working group, said, we believe we can make common pipelines. We can describe common pipelines. And we did not want to do that we did not want a standards body to create these pipelines, because that's too slow and it can be competitive, and, you know, when vendors, you know, behave badly, they can get their pipeline, you know, produced or standardized, and then they can obstruct every other pipeline, et cetera. So this is not a way to really drive innovation. What we wanted was for the participants in the community, the SDN software developers or the network operators, and potentially the device vendors, to be able to give, to bring models out and make them available to others. So then we have to figure out how to take these models and map them down onto that diversity of physical pipeline. But at least with those common models, now you've got an API that people can write network software, basically network applications on top of this well-understood interface. OpenFlow 1.0, you know, it had a common pipeline. Like I said, it was a trivial pipeline, but it was common, and that really did allow it, and it was also mapped. Essentially, the devices may have a very flexible table somewhere in their pipeline, and the coders would at coding time, do that mapping. That was typically the access control table in the device. So this mapping has done before, but it was a kind of a straightforward mapping. It was done at coding time, et cetera. So we're looking to make a model that says, well, we're going to have more than one pipeline, OpenFlow kind of expects all this stuff to get sorted out at runtime. You hook up two devices. They don't know anything about each other except that they speak OpenFlow, and the controller will send messages to the switch, and the switch will just deal with those messages. As I mentioned, when there's a variety of pipelines, that gets very difficult or arguably impossible for the switch to do with no advanced knowledge. If there's advanced knowledge, different story. So, I've kind of skipped ahead. I've already talked a little bit about this slide. Essentially, the early OpenFlow pipeline was a subset of all interesting devices, and the introduction of additional tables, which happened in 1.1 before the ONF came into existence, just before, or before it was launched, I should say. The new model was now a superset. So now it's more the other way around. Every ASIC is actually roughly some subset of the OpenFlow pipeline. On the other hand, NPUs, they could basically model whatever you wanted them to. So they can take the OpenFlow messages on the fly and figure out what to do with them and kind of adapt along the way. Having said all that, like I've already said, ASICs have interesting pipelines. We should figure out how we can make use of them. How do we do that? By not trying to solve this at runtime, instead we should be looking at these common pipelines as a way to sort things out in advance. Runtime turns out to be a bad time to do things from a network operator's perspective anyway. A little bit too many variables. What if that message that comes down doesn't fit? What if we can't process it? That should be known well before runtime. And the fact that ends up getting solved in some test lab or et cetera before, why would you solve it again at runtime? So let's create a model. Let's figure out that mapping between the control plane pipeline, that abstract pipeline that the control application is thinking about, and then map that down into the device pipeline sort of in advance. Oh, what does that mean? It needs horsepower. All right. Problem solved. IT department. Just a second. All right, so all that was about how do we map, what do we need models for, and how do we, we want to map them. So we want to map them from this abstract model, which forms a good development platform, a good basis as a development platform for SDN apps. And then we have to, in order to make that useful, this platform has to be able to run on the underlying silicon, and we should know in advance whether it will run and how to run it. So our first framework approach, we were kind of switch oriented. Our early approach was driven by, well, kind of a perspective of OpenFlow. It was really oriented toward the switch. The protocol is actually called the OpenFlow switch protocol. Most of the idea was, well, you got the controller, it's going to send these OpenFlow messages, and the challenge is to figure out how in the switch you deal with that. So we had that same viewpoint. Most of the participants in the working group were kind of device vendors, and there are a lot of controllers out there. So we didn't think in terms of controllers. The controllers were all over the place. And they were also not represented in the group. We didn't feel like we controlled them. We feel like our job was to just work things out on the switch side. And also, the OpenFlow picture was the controller tells the switch, and we were sort of still following that model, essentially that top-down model where the use case is pushed down into the switch. And so here, this is the picture of how we saw that on the early days. There would be a controller with applications above it. There would be some API or mapping layer. We're trying to create a common northbound API. There's more clarity there, but as you know, I think there's still not exactly a standard northbound API. But we imagined there was some northbound API. The idea was to standardize it. And so we would come up with a few use cases, not just us, but the community, the larger ecosystem would come up with use cases that were interesting. We suspected a lot of people already knew what use cases they wanted, and they would bring these use cases forward, and we would help them describe basically models for the pipeline processing, the packet processing, which we call TTPs. That stands for table type pattern. I'll mention why in a minute. And then in the devices, we would, if we believed a device could support a particular use case, we would put a mapping driver in the device. This seemed very much like very compatible with the early picture of OpenFlow. It was a little burdensome on the device implementer though. And this I talk a little bit more in the right away in the next slide. This mapping of doing this model to physical mapping in the switch had some weaknesses. So these are the challenges, but we weren't actually aware of them as we were doing this. I mean, maybe slightly aware, but we didn't really see alternatives. So we just said, we'll march on because we need to solve this problem. This is how we can see to solve the problem. And once we solve it, we'll have tools and things will be simplified and no one will mind because SDN will take off. So the problem was that switches are not a great place for code development. They're not like servers. They're not. You don't have like vast amounts of memory and large chips and the coding environment. You don't get to have as much control. And in addition, vendors are always trying to stick in new features. They do a code release typically every 6 to 9 months on their devices. And if we wanted to have support for a new model and have that stuck in the switch code, you'd have to wait for a long refresh. It ends up being quite burdensome. Going back to this picture, if we're going to have drivers in there, and remember these use case models, in the early days, they're probably going to have to iterate a few times, and they won't really know how to iterate until they try them out on a device. So basically, this model didn't support innovation very well. We want sort of an agile model. Switch software releasing doesn't quite support an agile model. But we hadn't quite thought about that. And also, essentially what it meant also is that, okay, well, what are the use cases that I will be able to support? Well, you can't really tell it at first. Which are the use cases that are going to be popular? Well, that depends, and so it puts the device vendor in this situation where they're trying to read the tea leaves and anticipate, and it might be a popularity contest, which use case to implement. Very difficult, having been a product manager myself for a while. How do I tell engineering which one of those they should pursue? Very difficult, and as it happens, there wasn't a lot of success driving that model forward. In any case, let me take another step back. How do we express these pipelines? How do we represent these pipelines? So I've been talking about pipeline models. I kind of showed you the PowerPoint version with the graphics. That actually is a way that humans really like to look at pipelines, much more than some of the text I'll show you. In addition, when we were forming our working group, we were told by the board at the ONF and the technical advisory group and so on, hey, don't rock the boat. Don't go changing the OpenFlow switch protocol. We can't deal with that right now. We're just getting OpenFlow off the ground. So this whole modeling framework thing you're talking about, that's all fine. Just don't change the switch protocol. Oh, okay. Well, that's very interesting. So how do we do pipeline modeling when we're kind of stuck with a control protocol? A control protocol is not a pipeline description language. So we ended up working backwards. We effectively figured out how you could, using the control messages, sort of infer a pipeline. How do control messages describe a pipeline? And so we essentially started thinking about, well, you know what? There's going to be patterns. Essentially, if somebody wants to do a particular thing, they want to do IPv4 multicast, or they want to do layer 2, MAC address learning, whatever. There's going to be certain recurring themes, certain patterns that we'll see in the tables and the matching and the actions. And this is where we came up with this table type patterns. We expected that we would see patterns, recurring patterns of table types. Well, let's just pin those down and describe them, and that'll end up being a model, and everybody's got this capability in their device. So it's just a matter of modeling that device, that model in their device. Table type patterns, and now we just need to describe those table type patterns in terms of OpenFlow. Okay, and we want to do that textually, etc. And we saw those as essentially what we're doing is we're constraining this space, this messaging space, this OpenFlow message space. It's a set of constraints. We agree on the controller side, okay, we agree, we're going to constrain ourselves to only using these messages on these tables, and then on the switch side, your constraint is that you have to agree that you're going to support these messages on this side. So when there's an agreement between the controller and the switch that yes, both sides support this model, and we had a whole mechanism for reaching that agreement. Essentially, if we go back a couple of pictures, the device in our picture supports some small number of models, and so it was just a matter of getting the controller to find out which models were supported, which models it wanted, and then they would agree. And then it would constrain the messages it sent to make sure that they were in agreement with the model, and the switch, by saying that it supported the model, was constraining, in a way, constraining itself to support those. Next, how do you draw these? How do you represent them? We wanted humans to be able to deal with this. We actually figured humans were going to be doing the mapping problem, the mapping from this abstract model, the model that represented what the use case needs, or what the application needs, to map that model into the pipeline. Basically, that's how driver code is written now, how that hardware abstraction layer is written now. It's written by humans. It's not compiled. It's not in some higher order language, really. I mean, it's in C, of course, or something that fits well into an embedded environment. But we also wanted machine consumption because we anticipated that we would want to do analysis on these models and analysis on these pipelines to compare and see which ones are common or what similarity or how they changed, etc. So we wanted this combination of human and machine consumption. We wanted it to be described in terms of OpenFlow concepts, match action tables, match fields and actions, and so on. But we had a bit of a bias toward the human, and so we inserted in the standard, the spec, we inserted syntactic sugar, and we used like short names and so on. The idea being we thought this would foster adoption the fastest, and there also were some things we weren't sure how to do from a sort of machine consumable perspective, and we also thought it would take more time, and basically we never knew if we could close on it. We actually thought there would be great value in getting a spec out there and getting feedback, and that turned out to be true. And we wanted to be able to express this in multiple languages like JSON or XML or whatever. Our examples in the spec use JSON, but we really did expect or intend for the spec to support other languages as well. And I think that kind of can. So here's an example of a JSON representation of at least the beginning. And a small TTP like this might run on for a couple of hundred lines. But if you're familiar with JSON, which I was not at the beginning, this is pretty, pretty sleepy JSON. Not that hard to track. JSON's a little easier to, it's not quite as decorated as XML in terms of the special characters, and so we kind of bias towards JSON. But XML is not that much different either. There's an object, a name, and a value. Pretty straightforward. And arrays are supported. XML respects ordering, JSON doesn't. That turns out to have some ramifications. Anyway, so we got this, we launched it, we published the spec last June of 2014, so about 16 months ago. The good news was before TTP spec was even produced, Broadcom came forward and said, hey, we think this is going to be great. They announced what they call the OpenFlow Data Plane Abstraction, OFDPA. But because it was before the spec, they published it in PowerPoint. They didn't actually have the JSON representation on day one. And they didn't call it a TTP because we were thinking about changing the acronym and changing what we called it. So when they launched their OFDPA, they didn't call it a TTP, which was sort of not the best way to build momentum. But pretty soon they came out with JSON, and then they also came out with a version 2, which was much more powerful. And it basically, the pictures that I showed before, the graphic images of pipelines are all from this version 2 of the Broadcom document. What's really great about this is there's no way you could control Broadcom chips with OpenFlow if you didn't have that document. Basically, there's just, as I mentioned before, there's just too much complexity, too many choices. You'd be guessing, okay, I'll send this message down, and there was no software on the other side that would figure out how to swallow it. So in some ways, it was this tremendous validation of TTPs. Oh, look at the immense power that's now unleashed in these Broadcom devices. We could never have done that before. Certainly, the single table OpenFlow couldn't let you do that. And so there's a validation there on the one hand. Also, we got some early progress in OpenDaylight. This I never anticipated, but Colin Dixon, who was at IBM and was active in the working group back in the early days, he disappeared from the working group when OpenDaylight launched. I didn't know why for a while because he was kind of behind the scenes. And then, boom, OpenDaylight burst forth, and Colin was one of the lead folks there, and at that time he was at IBM. About a year later he came over to Brocade, and he was still very interested in this problem. How do we actually map some kind of common layer onto diverse hardware? He really wanted to be able to do that from the perspective, he's a software guy. He's like the opposite of me. I'm this guy coming up from the ASIC side, and he's coming down from the software side. But we really saw this problem as in the same way, that we need to solve this mapping problem, or we won't be able to write SDN apps. And that's what we want to do. Or I want other people to do it. He wants to be able to do it. Perfect. Here we go. So he wrote a bunch of Yang. I'm still trying to get my head around Yang, but he just wrote a bunch of Yang. Effectively, it's a schema for TTPs. Boom, he's importing early TTPs. And I had no idea that was even possible, even though we had said, yeah, we want to support machine consumption of these pipeline models, right? These TTPs, we want to be able to consume those. I'm thinking, yeah, someday we'll write some kind of tool. If this isn't some kind of tool, this is a controller, and he's just going to import the TTP using Yang, and boom, he's off doing that. Found some problems, fed them back to us, and some of it we fixed and changed. Some of it he figured out how to work around. Now, one interesting thing there, though, is if you looked at our early framework, our picture was that we would have use cases, that we would have these common pipeline models, these common packet processing models that applications could write to, and then we would map those onto the hardware. OFDPA, for all its amazement, all its wonder, is actually the other way around. It's the device-oriented. It describes this device. It exposes a tremendous amount of value in a device in OpenFlow terms, but it won't work on somebody else's device. And it's sort of overkill for the use cases. In fact, it has many use cases embedded in it. That's why they have, I showed you just a couple of pictures. They have 7 or 8 similar pictures in their 300-page or 400-page data sheet. So this was a different model. It brought about a new thinking on the controller side because of the Yang tools, and basically new thinking on the mapping side as well. I should also mention that did I mention that? The OFDPA, the JSON, was not built directly by humans. It was built by tools as well. They entered a bunch of information in these massive Excel tables and ran it through an export, some export software, I think in Visual Basic, to generate the JSON. So no human was sitting there typing in JSON, which is at 20,000 lines or whatever it is. That would have been a bit of a project for a human. And no human was importing it into OpenDaylight. So we said, okay, we've been focused on the wrong thing. The humans like to look at tools, essentially. PowerPoint, sort of a tool. There's other tools. I have a picture of a tool, but it's tools like schemas, and schemas like, and they also like, the tools also like full OpenFlow.h names. So essentially, we were taking those names in OpenFlow.h that have long strings, and we were sort of stripping off the part at the beginning that we thought was kind of redundant. But in fact, if we matched up with the OpenFlow.h names, that would be better for OpenDaylight and other tools. They could just get the information out of the header file, map it to messages, etc. And then some of the clever things we thought we were doing for humans in our syntax were painful to represent in terms of schemas. So a lot of this is reflected in TTP 1.1 version, which isn't out yet. We're haggling and wrangling with that now. We actually expect, instead of delivering a English language version of the document first, instead we will deliver a schema first, probably open source that schema later this year. That'll be good because then it can be validated in OpenDaylight and various other tools. In fact, we'll do that before we publish it. We'll do some preliminary validation. And then we'll write the human English language stuff to follow on to that. But it seems like most people, the way things are going, they'll mostly want the schema anyway. And we'll add a bunch of examples as well. And I think there's going to be a repository of examples. We have a repository already at the ONF. This is an area where at least the ONF is now getting much more open, supporting open source. We have GitHub repository of models, that is to say TTPs, and more things will have repositories of schemas as well. So that's a great place for us to put examples as well. So the other thing the other kind of progress is, instead of just thinking in terms of that use case model that we started out thinking of, or turning our heads around and thinking in terms of devices, we now think in terms of both use cases and devices. This is a picture of, sorry, kind of a weak transition there. I forgot I was going to jump to this in between. This is a schema-driven editor. There's a generic JSON schema-driven editor, which we've adapted and are using as a TTP editor. And it's much easier to create and modify TTPs in this form than either in Excel or in JSON directly. So we've got this enlightened approach now. A lot of time has passed. We don't, the controller world, we don't have the 20 controllers, the 20 open source controllers that it felt like we had 2 or 3 years ago. There's other complexities about the controller world, but at least there's just 2 or 3 really leading contenders on the controller side. A lot of similar thinking in the controller space. Controller participants, like my company, are now represented in the working group. So now we can evolve our thinking. We can include controllers in our thinking. And also Broadcom's device-oriented model changed our minds as well. Instead of use case models or device models, we now think about doing both. Whoops, did I push the right button? I think somehow I've got the same slide in there twice. Sorry. I think the point was there, the bottom bullets. We put more work into the controller. We move the mapping function out of the device where it's difficult to do and put it in the controller where it's much easier to do, much easier to rapidly iterate code. Third parties can participate. Most switch vendors do not welcome third-party code to run in the box. So even if you're willing to do the code work, doing it in the switch is hard. Meanwhile, the switch vendors can now focus on what they do best. So that's what Broadcom did, right? In this picture now, this is a new model. Both kind of TTPs are pictured here. We have a use case TTP at the higher level, and then device-oriented TTPs at a lower level. And each device just supports the TTP, that is to say, the pipeline model that best represents itself. And this is good from the vendor perspective. They don't have to go chase after some elusive pipeline model that is sort of changing and may or may not be popular. Instead, they focus on trying to express their own capabilities as best they can in OpenFlow terms, the way Broadcom did. Meanwhile, yeah, there are still use cases, and we can map them to the devices, but we just do that mapping in a place where we can have open code, we can have algorithms, et cetera, et cetera. We can take advantage of things like Colin Dixon's Yang, and we can import TTPs, et cetera. How do you import a TTP into a switch operating system? Ooh, much more complicated problem. So this has really changed our picture. At the same time, there are flexible devices out there, like we said before, running network processing units or so on. we can still fit those into this model. So it's a much more complex picture, a little bit more feasible. We have a lot more interest in this model than we did before. And that's kind of where we stand right now. We are able to do some things. This picture that I drew is not really how OpenDaylight works today, but it's where we aspire to go. You might have heard about the Atrium project at the ONF, and there was some talk before my presentation about ONOS. ONOS has a similar idea. They don't call them TTPs. Actually, they do sort of talk about the southbound drivers as being TTP drivers. They don't use JSON. They don't import the models. But so they're hand-coded drivers that match to kind of device pipelines. The use case-oriented thing is what, well, we see a lot of similarity between TTPs in a use case picture and what the ONOS folks call, or Atrium folks call, flow objectives. And it's kind of a higher level, a little bit more abstract notion of the processing that you want to happen in a device or in the infrastructure, because you won't even say device. It's just, it's almost like a services abstraction layer, which is an OpenDaylight term. So this is where we're going right now. And the interesting challenge is that mapping piece. And this picture is not ideal, which I've learned just in the last few days in similar conversations, and I haven't had a chance to conceive a better picture. Essentially, really, this makes it look like a TTP or a model is a bunch of code, but it's not really a bunch of code. It really represents an interface, so it's more like an API, which would be more like a horizontal line, I suppose, in this picture. And same thing with this. The device-oriented model is also not a bunch of code. In theory, I suppose it could be a driver, but it's mostly really, again, an interface. It's an API, but a different API. It's these lines, which I envision as being maps, this mapping, that actually is where the code is. And so these boxes that think of as being code are actually more like lines, and these lines that I think about as being connections are actually code. So I have to redraw this picture in order to be a little bit more representative. But this is what's going on now in OpenDaylight. So this is the progress that we're having. The next release of OpenDaylight is called Beryllium. We expect to have our first stack of a simple use case and probably the Broadcom device model, OFDPA represented there. We're waiting for other players to come forward with device models. It should be easy to come up with use cases, and then pretty soon we get the ball rolling here. So this is where we stand. So finally, the problem statement. Am I out of time? Yeah, I'm not quite. Well, I started a few minutes late, so I've got 5 or 10 minutes. Okay, good. We need to be able to do this, basically solve this problem in a scalable way. There's a lot of interesting forwarding capability out there, and there's a lot of interesting forwarding that we want to do. Interesting forwarding, the use cases we can represent them in terms of pipelines. That's what the market's going to want on the use case side. And we have all these device pipelines that are out there. Very often we can map to them. Basically, I see the Broadcom model, the Broadcom TTP, OFDPA, as really expressing the ability to map use cases onto a complex pipeline. Right now, that's a slow process, but I believe it can be accelerated. How do we accelerate it? We're actually looking into how we do that right now. We've been thinking about this for a little while, but we're really focusing this thinking at the moment. So when we look at each of these models, it turns out it's not hard for a piece of software to map out all the possible pathways through a model. There might be one set of matches that happen in one stage, and it takes you to another stage, or it takes you to a different stage. Going back, well, I won't flip all the way back there, but in some of those graphics, you can see that there would be a choice coming out of a table. You could go to one of 3 different tables. Software can work out all those different possibilities. What are the different ways that flows can be processed? And in the OFDPA, in the Broadcom chip, if you combine all the different or use case pipelines into their massive device pipeline, there are really hundreds of ways. I think it's in the small hundreds, but there's hundreds of ways. If you look at a use case, typically there might be a few dozen ways, a dozen or a couple of dozen ways that different kinds of packets can be, will pass through. So you'll look at something, and it may be that the simplest path is topology discovery, right? So topology discovery, typically that's a controller sends out a link layer detection protocol packet, LLDP packet, sends it out, and on the other side, there's something to detect that packet and send it to the controller on the other side. So they're basically two controllers, or the same controller maybe, talking to itself using LLDP packets. So that's one kind of flow. It's not really mainstream flow, but that's kind of the way networking is, right? Well, there's all these support flows that run around in your network, all in preparation for the massive data flows. You know, the massive data flow is the one that consumes all the bandwidth, but there's all these, well, there's I sent a frame to the DNS controller, and then I had to do an ARP and all this other kind of stuff. There's all these little packets that you have to figure out how to process, and if you don't process those, you never get the big data flow, right? The big data flow is where performance is noticed and et cetera, and where the value is added for the most part. But you have to get all that kind of infrastructure support messages too. So that's why even in a fairly simple use case, you'll see 12 or 15 or 18 different ways that a packet passes through a pipeline. Sorry. So we can write software, and we're doing that now to look at, okay, this use case needs these 12 different, it needs to process these 12 different ways of processing flows, depending on different characteristics of the frame. What's the source, what's the destination, what's the protocol, et cetera. Tells you how to process it. Maybe there's ACLs involved, which port did it come in on, and so on. Then you can go look at the OFDPA or some other complex device model and say, okay, how can I use this complex model to process the flow in the same way? Because it's got all the matches and all the actions are described in this model, so we can map those together. Sometimes the challenge is that a simple processing pathway in a use case seems to map to 5 different, it's not surprised because there's so many different paths through the complex pipeline. There may be a dozen different ways it looks like you can map. So right now we need a human to kind of go, yeah, 10 of those mappings don't make sense. Cross those out. And then you may have to go figure out, okay, well, I'm not sure whether it's this one or this one. Let me go see how other paths map out. And when you map out a series, all the paths, then it becomes pretty clear. Look, no, I can't map it that way because then the other stuff doesn't work. This is the only way I can map it, and so on. So this is how it's done right now. We look at that and we do it as humans. So we map out all the flows on the use case. We map out all the flows on the device side, and we figure out how to tie them together. Once we've tied it all together, we can compare the two behaviors. How do we do that scalably? This is where the software comes in, and this is what I've already talked about. The utility that we're now building into OpenDaylight, and I say it's a utility, it's actually meant for developers more than it's meant for live operation of a network. But it takes advantage of that import mechanism, the Yang that we already had, so that we can import a model, a device model, analyze the different pathways through it, and then put 2 of those models side by side and let a human say, yes, I want this mapping, and then generate some probably Java code that will run that, or maybe some other kind of code. But can we do that? Can we maybe do that completely by machine and get the human out of the picture and make it scalable? Maybe the human's only at the end to validate it. So I just bring this picture back up to take another look at that. It can import all these things. We want to do it at this kind of a scale. And also I put this picture up because I think we're going to get back to it in a minute. And my proposal is to do header space analysis around that. Now, I said before, I'm not a header space analysis expert. But that is actually kind of how I think about it. I look at, if I'm looking at these 2 cases, I've got the use case model, and I've got the device model. When I've got the device, the mapping done correctly, the header space analysis of the 2 come out the same. So you put packets in, you try packets in a variety of header space, different addresses, different protocols, et cetera, all the varieties, different quality of service, et cetera. They will, if you put them through the use case model, they'll have certain outcomes, certain results. You should be able to get those same results when you run them through the actual device model. And the device model, of course, needs to represent how the device works. So this is where we are right now. This is the point we've achieved. And now it's like I want to call on the header space analysis experts to come and sort us out, teach us how to do this, help us figure it out. And now I'm kind of excited about this now. Once again, I mean, I think SDN is basically born out of academia. Now it's a chance for academia to come and save us as we've tried to implement SDN. So do the header space analysis on the both of them, and this will really move us forward toward a more scalable model of model mapping, a scalable picture of model mapping. And I have Q&A as my next slide, but I guess I'll ask first if we have time for Q&A.
Yes, I think we can. I think we have time for some questions.
Okay. Oh, and now does it turn out we have two mics after all? Excellent.
Hi, Kurt. Thanks for the great overview. I have two maybe interrelated questions. Can you comment? Yes, this is the picture on what is going on the top of the fully abstracted northbound interfaces. What is going on? Can you comment on anything promising there? And the second question is whether you see opportunities for convergence between what P4 and the compiler like a top-down approach and the TTPs or initial bottom-up. Do you see opportunities for convergence in an intermediate layer there?
Yes to both. So we can talk about both of those for a second. And in fact, I was tempted, back when I was first approaching this talk to try and cram all that in. And then I realized that was probably not realistic, but it is something we can talk about just for a quick minute. On the fully abstracted northbound interface side, I mentioned earlier that ONOS has this notion of flow objectives. OpenDaylight has what they call service abstraction layer. They're kind of similar in a way. In fact, OpenDaylight calls it a model-driven service abstraction layer, which is why it has that Yang modeling capability. Essentially, right now it's the upper software still has to think about devices. Maybe we can abstract the devices a little bit so it's kind of a generic device, but it's still a device. Moving more toward flow objectives is more, this is the outcome I want. It's not necessarily saying how to do it. In other words, it should look more like a service. So I think of the flow objectives and the service abstraction as being common ideas. So you say, don't allow this kind of traffic to go to this kind of to go to these nodes in terms of maybe address space, and you're now talking to the network instead of talking to a device. And it's up to what I think of as the operating system to figure out how to map that down onto the infrastructure. And in many cases, that may be represented in a virtual terms anyway. And we don't have to think about virtual devices. We just think about virtual capabilities, virtual services. So there is progress there. I'm abstracted a little bit away from the northbound interface right now, but I see that coming together. I see the work that came out of the Atrium project, where they were going to show how to do it, and I think they did sort of show how to do it, but they basically demonstrated that we still need device-aware code. And so they kind of showed us, which some of us already knew, that, yeah, we weren't quite there yet with device independence. I don't feel like I completely answered your question, but part of that is because I got about as far as I can go. With respect to P4, and my working group has multiple threads, so it has the protocol now. That was one of the reorg things, is OpenFlow protocol is now in our working group. The models, today's models, which are TTPs, are in our group, and then what's called next generation OpenFlow, which is not a very good name, and we all kind of know it, but there is no good name, is toward like future models. And what's interesting is just like I said before, OpenFlow is actually a control protocol. It's not a pipeline language. P4 is the opposite. P4 is a pipeline language. It's not a control protocol. So there's actually a nice complementarity there between P4 and OpenFlow. P4 doesn't specify a control language. It could be some version of OpenFlow. I mean, there's some things maybe missing in OpenFlow right now, but we could have OpenFlow 1.6 or 1.7, and that's what we're currently talking about. But that still doesn't quite answer your question. Essentially, TTPs are really more the pipeline description model of today's OpenFlow, and P4 is the pipeline description model of tomorrow's OpenFlow. So is there a way that we can transition from TTPs into P4, or maybe P4 into TTPs? How do those things coexist? And in fact, we've had discussions about how we need to describe that. We need to answer that question almost in marketing terms to explain to the outside world, the community, how we see that going forward. So we've had some discussions internally about that. And we did look at it both ways. At first we thought, well, we're gonna figure out how to take P4 and translate that into a TTP. Well, that does turn out not to be the right way to do it, but it's fairly straightforward to talk about going the other way and you could take a TTP, run it through the right kind of compiler, and generate P4. I think that's very important, in part because I think we're 90% of the way there. We need the other 10%. It might be that we need to change P4, add some features to P4 to make sure that that's possible. Especially across, partly we have to finish TTPs, which we're still doing, and then finish P4 to make sure that we can do that. And the reason I say that is that the same people that are going to be deploying OpenFlow now and SDN now are the ones that are going to be deploying P4 and so on. So it's not going to be a greenfield kind of opportunity. If you try and go greenfield with P4, every device has to be a programmable ASIC and all these other kinds of things. It makes it very difficult for an adoption model. Very high risk, big investment. There's no incremental option. If you combine it with the TTP model, as you suggest, now you have a kind of an incremental approach. The same people that were looking at SDN before are looking at next-gen SDN, et cetera. So that's exactly how we're thinking about it now. It's not what the P4 people are thinking about, because they're more focused on trying to solve the problem. And we're kind of a step back going, okay, once they've solved that, how do we go about driving adoption? And so we're talking about compiling TTPs into P4. And then you compile it again into the ultimate device. So that at some level solves the mapping problem. But I think most of the compilers will be compilers for programmable devices. And for a long time, most of the deployed devices will still not be programmable. So this kind of coexisting world between TTPs and P4, I suspect, will be very useful and kind of durable for 10 years, 5-10 years. One more?
I am a controller developer.
Which controller?
Our own. It's on the
okay.
poster. Okay, it's Ranos, called Ranos. We had a lot of POC in different areas: telecom operator, data centers, enterprise. And I've got one simple question: why Broadcom doesn't just simply create a chip with like multiple real TKM OpenFlow table, and that's it. That's what we need, because technically, in real hybrid switches, we have some limited ACL tables, just one. Someone tried to produce us multiple, but like MAC table, but only MAC addresses, but a lot of flow tables. Next one is like ACL, but only like 1,000 flow entries and etc. So it's a little bit tricky, and why just simply create like tens real flow table? Is it expensive based on TKM, or why?
Yes, and I would guess that you've read the white paper that was written by, not white paper, but it was a paper that was written a couple, 3 years ago maybe. Nick McEwen, a bunch of people that were at TI at the time. I'm trying to remember what the tag name for that. It was, I'm sorry, but basically they did some analysis and they said, we think you can build these programmable ASICs with essentially TCAM-like behavior at every stage, and you can reconfigure it a little bit. And they thought they could, their argument was, their claim was they could do it with only a 15% increase in area. There are several gotchas, yeah. I mean, it might be doable. TCAM is very power hungry, and there's a lot of pressure to keep power down on individual devices, but on the data center as a whole. They consume a fair amount of area as well. So if you do, say, a MAC lookup in TCAM versus a MAC lookup without TCAM, most MAC lookups do not require TCAM. They don't need that kind of flexibility. You could get maybe 2 or 3 times or 4 times as many MAC addresses in a non-TCAM memory. So if you know you're going to do a MAC lookup, you're better off, you know, people now want to have 128,000 MACs or maybe 256,000 MACs. You can get more MACs in a non-TCAM table. So that's a trade-off. And then there's the power trade-off. And they don't clock as fast. TCAMs don't clock as fast. Many customers, especially finance, are very, very concerned about latency. So that's where they sell a lot of boxes there. So I'm sure that Broadcom has looked at it. I haven't actually had this conversation with Broadcom. The paper I was referring to was TI. And TI did this analysis, and they said they believe this was possible. The other comment I was going to get to is 15% area increase. It's funny how they put it in the paper. They said 15% area cost increase. Well, which is it? From my perspective, is it area or is it cost? Because a 15% increase in area is like a 25 or 30% increase in cost because of yield ramifications and so on. So if you get to a 30% increase in cost, your market share just went way down. You know, I'd rather take the ASICs, thanks very much. And as a result, when the volumes decline, well, then the costs go up again. It's this interesting, you just fall off the cliff. And so you could maybe build that chip, but it's hard to tell if somebody would buy it. And if you look at today's SDN market, it's not like the MPU sales have just exploded, right? So if you really want a device that can do anything, why aren't MPU sales really taking off? So all that's the business argument, combined with a little bit of a technology argument for why Broadcom doesn't build that. In fact, maybe they did. Maybe it's in their lab somewhere. Why didn't they productize it? Maybe they will. They probably wouldn't tell us if they were 6 months away from that. Well, maybe they would tell us if they were 6 months away from it. The other ramification about this is that the SDK, the software development kit that you need for that, is a radically different SDK than the one they have now for their ASICs. So they'll have to develop that kind of from scratch, and they'll have to work for their customers, and they have to do this huge investment, and then you have to go talk to the vendor and say, yeah, we've got this whole brand new tool chain, pretty sure it works, we want you to deploy it in a greenfield, you know, very broadly, spend a lot of money and buy a bunch of it, and there's no software yet that's available to run on that, but there will be soon, trust me. So it's this adoption chicken and egg problem. Now, in fact, of course, Barefoot Networks is, I assume you're familiar, you've heard the name. That's exactly what they propose to build. Who do you suppose is going to buy Barefoot Networks? Right? So that's how Broadcom's going to build that chip. That's my view, or maybe Intel buys them first, or maybe Intel introduces that chip. So.
Actually, the last question.
Yeah, that was a good panel question.
Okay.
I'd love to hear other people's comments.
Thanks a lot for presentation. Additional question regarding SICAM to continue discussion. So basically, one of the basic things that should be implemented is multi-field classification, as you said, by using SICAMs. But if we consider a virtually centralized model that we know end-to-end basically behavior, why do we need multi-field classification? We can just enumerate all potential computation paths, use global label. We can use all existing, basically already existing in the market, ASICs for MPLS lookup that just do direct access with exponential memory and 13 bits. It's enough from scalability point of view. You need to do nothing. So basically, why just OpenFlow and all this basically attempts to standardize southbound API, attempts to represent them on fast path as multi-field packet classifier?
So that was a complex question in a way. So I actually agree, and it brings up another point. You know, so in parallel with this SDN development, there's there's been NFV, and in fact, early SDN, it seemed like a whole bunch of that was in the OpenV switch, right? So right at the edge. In fact, so much on the edge that it's up in a general purpose processor. It's not even, so why not in that general purpose processor do that tagging that I think you were referencing, where you say, well, you got this multi-field analysis, do that one time, slap a tag on the thing. This is what you're getting at?
Not really, since all these ASICs are significantly faster than basically general purpose CPUs. So, but all of them can do MPLS lookup. And if you have MPLS lookup, you can do all computational classes, since and you need to change nothing, and you can enumerate them.
So this is more the PCE approach then. Yeah, I mean, I was saying doing it in the OVS is right at the edge, and so you're not doing it for the entire network. Yeah, that is a more, and I don't know if I've thought about it in the terms you're talking about, so I don't know if I can answer that exactly. But in answer to the earlier question about why doesn't Broadcom do that, I think the fluidity in the space around NFV, like, okay, so what's going to be done in hardware and what's going to be done in software anyway? We don't even know what's going to be done. You know, the question for the panel, is it SDN or is it NFV? I mean, I kind of think it's both. I kind of think tag switching still makes a lot of sense. I do think the really complex multi-layer, you know, layer 4 through 7 stuff will be more inclined to go into an NPU, I mean a general purpose server for lots of business related and reasons, which is why NFV anyway is going. It's different logic, but it makes sense. And it does change what you expect the hardware to do. You know, I think there was a while, and I heard people talking about this, maybe we'll just get rid of switches altogether and it'll all be servers. And it kind of goes, well, that doesn't make any sense. I mean, you know, a really powerful server, now you can get 80 or 100 gigs through a server, but if you go take a pretty powerful Broadcom chip, I mean, there's a terabit of bandwidth in a Broadcom chip. So to your point, you know, yeah, those ASICs, they're really fast. Even though, yeah, servers are, I mean, go back to when I was getting in there, we were moving routers out of servers into ASICs because the ASICs were faster. They're still faster. You can do amazing things in servers. Servers have gotten a lot faster. So have networks. You know, we need to be able to do this terabits thing. So I think a lot of processing will happen in servers. I don't think NFV is going away anytime soon. We still need a lot of stuff done in ASICs. I think tag switching makes a lot of good sense. I think the protocols will emerge. And so I think that's the other problem that's happening for Broadcom is if you look at where this settles, when the dust settles, you know, maybe we don't need all that programmability after all. What we need is, you know, a certain kind of programmability, a certain extensibility for one massive lookup, and then after that it's just tag switching, you know, so it's a piece of cake. Now you're really trying to read the tea leaves, but I think that's a perfectly good question, and I guess we're out of time.
Yeah. So actually, we are running out of time, so please allow me to conclude this session. So let's thank Mr. Beckman.
Thank you, and I'll be around in the panel. So.